Hi, in 5.3 question 14, we've got rectangles being drawn in a different orientation. So if I wanted to work out this area and split it into little rectangles, the width of each rectangle is now not a dx value, but a dy value. The thickness is along the y-axis, or the width if you like. So what I've got is the sum of little rectangles making up the area, just as we had with a different orientation. The height of your rectangle is the biggest x value, that would be the curve, minus the small x value. In other words, the right value minus the left value. The left value here is just x equals 0. And the right value is x equals this business. So my rectangle height is just given by this function expression as a function of y, and the width of each rectangle is dy. I'm integrating from y equals 0 to y equals 6. We just use rules of integration to work this all out because there is a match of the letters. So this works. And plugging in your numbers, first the 6, and then the 0 is going to give you an expression like that. Right, moving on, question 15 asks us about it's about untrapping a function from being a derivative. So you've got an expression, a dash expression, written like this, says that it's the derivative of this thing with respect to that one, dw dt. And here we've got a weight measured in pounds per year. The per year is the rate part. And if I integrate a rate with respect to that letter there, can unpack it like this. Algebraically, you can imagine these dt's sort of cancelling. You're left with the integral of dw, and over here there's an invisible 1. So the integral of 1 dw is just w, and if you wanted to do that as definite integral from 5 to 7, you would be getting the value of w at 7 minus the value of w at 5. So if this is looking at a child growing, and t is measuring time in years, we're looking at the weight of the child when they're age 7 minus the weight of the child when they're age 5. If this was to be the decrease in the child's weight, then it would have been defined so that as time goes on, the value that you're looking at here is what the decrease is. But normally, if all goes well, the child's getting bigger. So we have the weight when they're 7 years old will be a bigger value compared to that, giving me a positive value, which I would then interpret as the increase in weights. Which, if this value, W7 minus W5, is a negative value, then I interpret that as the negative increase in weight, which is then change the sign of the number and call it the decrease. But because you would have to change the sign in the number, I couldn't define this value as being, the number value that you get is not the decrease. So the answer would be, well, you'll figure it out. Okay, question 16. Beware that you are looking at displacement, not distance. See question 1. Question 17 is again like question 15, to do with undoing a rate of change. You've got a rod with length 4 meters, so from 0 to 4 is my x values. I'm integrating this rho, which is the rate of change of m. If I integrate the derivative of m, I'm going to land up with m. Nice singing in the background. Question 19, we've got a function f is greater than or equal to g. Here are two possible pictures where my yellow graph is above the green graph. And I've also got the case where the slope of f is greater than, in this case I've written in greater than, the slope of g. So between a and b, I've got to have the yellow graph on top of the green graph. The y values of the yellow graph are bigger than the y values of the green graph. And then for the slopes, I should have the slope of the yellow graph bigger than the slope of the green graph. Here they're both positive, but the yellow one is more positive. Here the yellow one is 0 and the green one is negative. So I still have this condition being satisfied, but I can give a counterexample. I can have where my if part is true, like that. Yellow graph is bigger than the green graph. But for my slope, I've got a slope value here of 0, I've got a slope value here that's positive. So it does not always follow that if f is greater than g, that f dash must be greater than g dash. Here is a counterexample. So one counterexample makes that not a always true statement. So that statement must be false, because they're saying here it's true in general. If this, then that. And then finally, if we've got a continuous function, and I want to differentiate the integral of a function, do I just get the function over there? Does the integration undo the differentiation? The terms and conditions that apply here are that your endpoints should be variable. Well, one of them should be variable. One should be a constant. You should go from a constant to a variable, and then this would have been the function at that top variable. But if a and b are constants, then what this part is over here, the integral, this definite integral, is going to return you a number. The derivative of any constant number is surely not a function. Cheerio.